Hello everyone. In this lecture, let's discuss about time dependent case. Now, before going to time dependent case, let us take a quick review of the time independent cases. Okay, one simple example of time independent case is particle in a box. Independent case. So, what did you learn in particle in a box? So, point number one is that your wave function for particle in a box was such that we can separate it into the spatial wave function and the function that depends on time. So this was possible because of the time independent case, and then we can easily write h psi of x is equals to e psi of x. The reason we can do this is because the time gets separated and this is true. And then what happens is that the Schrodinger equation also looks like I h cross del by del t, even though you can write it in the full wave function which is x and t, but since time goes off, so it simply becomes this. You can write h psi of x. Okay, so and what is this extra f of t? So this looks like this, e to the power minus I et by h cross. Okay, so there can be h, but when the h uh, acts on the wave function, you get when the h operator acts on the wave function, you get e. Okay, now this is the fundamental idea behind the time independent case. Now there is something quite interesting. Now I can actually prove that this actually helps in the evolution of the wave function. For example, given you know a wave function at 0, then even if at time t equals to 0, then how would the wave function look in time t equals to t? How the whole thing is going to evolve? Now in time independent case, specifically in the case of the particle in a box, such kind of evolution doesn't make sense, because even when you evolve them and you calculate the probability itself is independent of time. But that doesn't mean that the wave function is not evolving. Just because that the time part has got separated out doesn't mean that there is no evolution. There is indeed an evolution. So basically I can write psi of x at any time t is evolving through e to the power minus I h t by h cross psi of x and 0. So if the wave function starts at time t equals to 0, then it moves to time t equals to and then the wave function at time t equals to t evolves through this equation. Now question is, how did we know that this is the actual evolution in the time independent case or whatever? This can be simply proved in a different way. Now remember that if I just use psi of t to represent particle in a box with n being various levels, so n depicts various level, then I can just use this state vector. So this is the state vector that represents the particle in a box. Okay, this is clear. And then to go from the state vector to the wave function in the position basis, you can do this. Then what you get is this. So here n represents various levels that you are dealing with, but n is not important in this case. So my main motivation, I want to prove in the time dependent case this thing, and then we will move to the time independent case and we'll see why things are not as good as what we see in the time independent case. So you have this Schrodinger equation, but then I'm writing the Schrodinger equation only for the state. So you have only psi of t, okay, and then you have h operator acting on psi of t. Now you would say, what is the Schrodinger equation that I know? It's quite simple to derive. You take x both sides, you multiply both sides in this manner, and then you can have the usual looking Schrodinger equation that you were familiar with. So what happens in this case? The x goes in, x out, and then instead of the state you get a wave function which is psi of x and t, and here also you get h comes out, psi x and psi of t, you get a wave function psi of x and t. So what we did here is that we used this property which converts the states into this wave function, which are functions of both space and the time part. So I can either work with this and this equation, or I can work with this equation. Anything is fine, but I'll work with this equation because it's very simple. I don't have to write psi of x and t again and again. That's the beauty of the Dirac notation. Now let's try to solve it in the time independent case. Why I'm calling this as the time independent case is because the Hamiltonian is not a function of time. The Hamiltonian is basically independent of time, and it doesn't change with time. That's the whole idea. So the Hamiltonian does not change with time. Okay, this is a very important stuff to be remembered. But now let's look at this derivation. So what I can do is I can have d psi of t, and then I can move the other psi of t here, and then this will become minus I by h cross the h, and then I can simply integrate from 0 to t d. And why I'm doing this particular derivation, though it is simple, is because I'm going to touch the same thing in the time dependent case, and I'll show you what are the problems that we face in the time dependent case. Then things will be much easier to move to the perturbation theory in due course of time. Now what do we get here? We get logarithm psi of xt, psi of t, and it should be at 0 and t. And since the Hamiltonian is independent of time, look at this important fact, it comes out of the integration, and then you get just t from 0 to t. Okay, and then what is this thing? This is nothing but logarithm psi of t minus logarithm of wave function at 0, and this becomes minus I by h cross ht. Okay, and then what comes off here? We can write uh, ln psi of t divided by psi of 0. So this is a wave function at time t and time 0 minus I by h cross ht. And if I take exponential both side, move the psi of 0 on the other side, then I can see that psi of t becomes e to the power minus I by h cross h of t psi of 0. So any wave function, if I know the wave function at time t equals to 0, I can evolve it and I can have a wave function at time t equals to t. But it doesn't mean, but you see the nature of the time evolution is such that when you calculate the probabilities, these exponentials they get cancelled, and that's why the probabilities they don't evolve with time as in the particle in a box case. But on the other hand, the wave function do evolve with time. Okay, but the fundamental idea behind the time independent case is not that the wave function is evolving or not evolving. Wave function always evolves. The main idea is that the Hamiltonian doesn't evolve with time, and since the Hamiltonian does not evolve with time, the probabilities they don't evolve with time. That's a consequence number one. And also the eigenstates of the Hamiltonian, the eigenstates of the Hamiltonian are energies that we already saw before. They also do not evolve with time. So things are very beautiful. But what happens when you enter into the time dependent Hamiltonians? So what is the main problem with time dependent Hamiltonians? Let's look at that. So time dependent case. So when you are talking about the time dependent cases, we are actually talking about Hamiltonians that are dependent on time. So what is the issue that we face here? So first, one thing that needs to be understand here is that when you have a Schrodinger equation like this, so I h cross del by del t, you have psi of x and t, and now you have a Hamiltonian of which changes with time, psi of x and t. So what happens in this case is that these kind of equations are very tough to solve because the h is now a function of time, which actually creates a lot of problem. And what kind of problem it creates, we will look. Now if I write it the same equation, if I write it in a very simplified state cat manner, then I can remove the space part and I can just have a Schrodinger equation that looks like this. Okay. Now mark the difference. The Hamiltonian here is a function of time. So if the Hamiltonian is a function of time, that means the concept of eigenstates becomes very tough. Or you can think of the energies, they don't there is no independent so eigenstates and eigenvalues are not specific, cannot be specifically found in these cases. Now why? Because you see, so assume that your h of t can actually have eigenstates and eigenvalue. If you assume it, then you are telling me that I can have wave function h as a function of time, and I can act them on this, and I should be able to get some e, maybe it's a function of time, and the same state back. But there is a problem. There is a very interesting problem is that since the h evolves with time, so you don't know at the next moment what the h looks like. It may look like a very complicated stuff, and then this thing that you found doesn't work for a different time. So either you can talk about the eigenstates at a particular time, so that means you can have an eigenstate at t equals to 0, and then you can have another eigenstate at t equals to 1, and they can be different because the Hamiltonian is itself different with time. So this is problem number one. But there is one more interesting problem that is lurking inside, which is a very fundamental in nature, is that let's try to solve this and look at the evolution. Now it's very simple. Now in the last case, when you solved it, you got psi of t is equal to e to the power minus I h t by h cross psi of 0. You found this, right, when it is evolving from 0 to t. So this is in the time independent case. But in the time dependent case, there is a very interesting thing that happens. This integration that you find, and here you cannot have the h outside this integration dt, because now h is a function of time, so this guy remains. And then in the time dependent case, what happens is that your psi of t now looks a little bit weird, because now you cannot take out the integration. I mean, it's not easy to solve the integration, and will come why it's not easy to solve this particular form. So you get this t prime and then psi of 0. So this is how the wave function in the time dependent case evolves. Okay, you have this, but this evolution operator, I mean u, we usually have this evolution operator u, right, u of t. So this is actually very difficult to calculate, or this cannot serve as a nice evolution operator in the time dependent case. Why? Because the Hamiltonians at different time, they do not commute, and that's a big problem. So this is not possible to solve, because the Hamiltonian at different times, they do not commute. So what do I mean by that? I mean what I mean is that the Hamiltonian at time t equals to 1 is completely different from the Hamiltonian at t equals to 2, because the Hamiltonians are dependent on time, and they can be very different, and as a case they do not commute. So when you have a Taylor expansion of this thing, then you will see that you will encounter a lot of problems. But before delving into that, let's try to understand what do you mean by the fact that when you have a time dependent Hamiltonian, the Hamiltonian at various times, they do not commute. What do we specifically mean by this? So what do we want to show? We want to understand why am I saying this, that h of t1 and h of t2, they do not commute. What do I mean by this? Let's try to understand. So let's try to understand using a simple example. So in this example, we will consider a spin half particle, and this is the example that is always being used and very simple to understand. So spin half particle interacting with magnetic field. So there is spin half particle and there is an external magnetic field that is a function of time. So in this case, the Hamiltonian is a function of time because the magnetic field with which the spin is interacting, it's changing with time. Okay, so this is your Hamiltonian. Chi is a gyromagnetic ratio. So what is S vector? S vector are the Sx, Sy and Sz, and this is well known, and we also know how these are spin angular momentum are related to Pauli matrices. So let's look at the fundamental problem that arises. So consider at t equals to t1, then B at t1 is such that the magnetic field acts along the x direction. So the magnetic field acts along x direction. So when the magnetic field acts around the x direction, then this guy becomes the magnetic field along x direction, so Bx. So I can write this vector in this way. So when I write it in this way, what happens to h of t1? So h of t1 looks like this. So it will be Bx Sx, and why there is Sx? Because in this dot product, since By and Bz are 0, so in the dot product this Sz and since By and Bz are 0, so Sy and Sz term also vanish in the dot product, and you are left with only one term. So let's try to understand what this is. So B vector has three components, right? So this is kind of like an S vector or S cap, and B vector has Bx, By and Bz. So you can think of these two vectors with three components doing the dot product. So this is point number one. Point number two, at time t equals to 2, it may happen that your magnetic field is now acting along the y direction. I mean, nothing stops it, right? So magnetic field which is acting on the spin now acts along y direction. So when the magnetic field acts along the y direction, what becomes of the Hamiltonian? It looks like this: minus gamma By Sy. Now there is a big problem. If you look at this derivation carefully, and if you try to now find the commutator between h of t1 and h of t2, you find that, and it's very easy calculation, because at the end you will end up with a term like gamma square Bx By, and there will be a commutator between Sx and Sy, and we know that this term is not equals to 0, because when you do the commutator between Sx and Sy, what do you get is that you get IH cross Z. So as you can see here, that this is a simple example where I have proved a case where the Hamiltonians, that at different times they may not commute, and this is the fundamental issue with the time dependent case, that the time evolution operator, the operator that actually is responsible to evolve the wave functions, they are not as simple as it looks in front of you because of this fact. So now let's try to understand a little bit deeper why this kind of commutator is creating the problem. So assuming that your u of t, so this was the operator, so assuming that your u of t, and it was in the exponential form, which is e to the power I by h cross a, and there was an integration from 0 to t, so h of t prime dt prime. So what is the fundamental problem? Let's look at it. Let's do the Taylor expansion. How does it look? So it looks like 1 minus I by h cross integration from 0 to t. So this is the first term, dt prime, and then the second term, which is actually the term that creates the fundamental issue, is looks like this. So integration from 0 to t, you have h of t1, h of t2, dt1, dt2. Now the problem is this: since the Hamiltonian at different times they do not commute, so this particular expression, the value of this particular integration will be different when you have h1 first and ht2 second, or if you interchange ht2x first and ht2x second, it can so the evolution of the wave function can actually be different. So it's a similar case occurs in rotation, right? If you remember, so what does Hamiltonian do? What does this time operator do? The time operator evolves the wave function. So in the Hilbert space, the wave function, when it evolves, it basically some kind of rotation is happening. So, and you know about rotation, that if you rotate a particular stuff in one way and then in the other way and then you reverse it, you do not get the final outcome similar. And this is a fundamental problem in rotation. You can learn about it. So the same thing happens here. So the ordering of the Hamiltonian, they actually change how the wave function, what is the final state of the wave function. So that is the fundamental problem. So and then how to get out of it? Well, one way to get out of it is maybe instead of studying the time Hamiltonian operator, which are hardcore like h of t, what about we study a more simplified form of time independent Hamiltonians? And the simplified form is that maybe the actual Hamiltonian is a time independent one, and the time dependence comes from an extra term that is added to it. So we will see that these kind of time dependent Hamiltonians will be easier to study, and that's why we study this, and we call this as the time, and we'll study this using perturbation theory. So and such kind of Hamiltonian, the study of such kind of Hamiltonian under perturbation theory, we call it as time dependent perturbation theory in quantum mechanics. So let's discuss it in the next lecture. How do we go about this?